Okay, so here we will be getting into how the dragon colors can be so distinct, even though they go by a genetic law here. So right now, I've got 5 different genes with an average of 3 to sometimes 4 alleles in each one, and it shows the likelihood of the fire dragon species to inherit each one. The earth or nature or light or dark, any of those other species, they would have different numbers for generating the random starter characters. Random starter characters are ones where you do not already have the parents written down, or you just want to start from scratch and you want it to be random, which is what I always kind of start with at first, though I like to work with the generation after the random ones because I like to put together the genetics and breed them. You know what I mean? It's kind of interesting. Okay, so let's get into this and start with the first one in this one. It's the color, just the color. And let's say we're doing the female, we're doing the mother who's going to lay the eggs. And we'll do the name and everything else later, but let's just say this one is a female. And we'll name her when we're done. And we'll make the color based on chance. What we're going to do is we're going to go to a number calculator. We're going to random number between 1 and 100. And we're going to go to this site. I like this one. And I don't count the first one that comes on the screen. I push go, and that's the one I use first. So we're going to do 2 numbers, 84 and 48. So we go back 84 and 48, 84 and 48. Both of those are above 40. So that means that this one has 2 red alleles. So no matter what the others of these say, this, unless they get a grayscale gene, this one's natural colors will be red. The mixing genes aren't going to be affecting her color because she doesn't have any competing colors like blue or yellow in her genome. So while they won't be expressed, we're still going to calculate the mix because that will be passed on to her offspring. And so what we are going to do is we are just going to look at the numbers here and just write that in her genome. Now, if she had competing colors and we don't know what her parents were, I would just do the calculation again. Make the darker color, like red is darker than yellow in my opinion, and blue is darker than them all. So I would just make the darker color an odd number, and for the even number, the lighter color. And that's how I would calculate that for our randomly generated ones that have no parents that we know of, since this is affected by the parents. Now, how this is affected by the parents, let me explain that before I go calculating, is the F on the top will calculate as to being more towards the father's color. So if the father was blue and the mother is red, the purple that the baby would be more the father's color, and FF would make more of a very bluish purple, while an F neutral or FN would make a more toward the father still, but it would be a little more towards the center color, more towards 50-50, if you get what I mean. And then, of course, an F and an M, which means taking after the father and the mother, would equal the same as this E here, meaning even mix or 50-50. So whether you get an EE or you get an FM, that both equals 50-50 mix, pure purple, same amount of red as the blue, and vice versa. If it's even mix and the mother, you start from 50-50 and go about a third of the way between 50-50 and the mother, 2/3 of the way if it's you know what I mean. Okay, that was a little bit misleading there. I'm a little lost now. I'd have to watch it being drawn to give you a better example with the bar. It's much easier with the visual than just thinking of the words to say. I know how it works though. And anyway, that's how you calculate it. Now the S is rare, 1 through 4. If you get an S gene, 2 of them, then you will have, let's say the red and blue example again, a split between red and blue in even patches, kind of like a calico or a tortoiseshell cat. You will have half of the dragon in random patches colored in red and half of the dragon colored in blue. But if it's mixed with any of these, then the mix is more of a mix of purples. I will get into that as we go, because this little thing can get wild. Alright, so let's calculate these numbers. Okay. 22 and 70. Remember that, 22 and 70. So, 22 is within the M range, which is after the mother, take more after the mother, and 70 is within the E range, so it's E and M. That is what she inherited. And then, welcome to part 2, where we will be looking at the mix colors. Welcome to part 2, where we will be looking at the brightness genes. Okay, so the brightness genes can affect any color, whether the genes are both red, blue, or yellow, or they have conflicting colors. Whatever color it is, it will brighten it, or darken it, or leave it in the middle. So the ones that control the brightness are B for bright, M for middle, and D for dark. These can make 5 different categories of light and dark, because if you have 2 B's, it's all the way at the top corner, and 2 D's is all the way at the bottom corner. Middle is, of course, middle, and M and B would be almost to the top and above the middle, and M and D would be between the middle and the bottom. Just as you would think, and B and D would make the same result as 2 M's, right in the middle. And that is how that one would work. And so we'll see how this red will be affected. Let's go to our handy little calculator. 62 and 54. 62 and 54. So that's, both of those are within the bright range. So this will be a bright red. Now see how this goes? It's pretty easy so far. Saturation, this will also affect this dragon a lot. It shows whether or not it will, stay the normal bright, or perhaps turn into a pinkish color, or perhaps a more grayish, or, it affects it in many, many different ways by affecting the saturation. So let us begin with that one. Hold on. Well, sorry, I actually got distracted there. Somebody was knocking on the door, so I have to run these numbers again. I know they'll be recorded, but I can't just go and watch it right now, so I'm just going to do these calculations again. Let's see, 69 and 64. That totally, made a whole different solution. 69 and 64. They're both over 30, so that's going to be top saturation. Whoops. Yeah, so both S and grayscale. Now this you would think would be like saturation, but it is not. So grayscale will affect whether or not it will be a gray, black, or white dragon in the grayscale level. There will usually be no tint unless it is mixed with the submissive N gene. Now, I say submissive because even though everything blends, all the other genes will automatically throw the dragon into a grayscale mode. Now, it is most likely for a fire dragon to inherit the N gene, which is, it'll neutralize this and it'll express normal color. But all of these others, if it inherits one of these in the low end of things, then it will change. So if it is N mixed with any of these, then it'll be off that color, like N and W will be off-white, and whatever normal color it would have been without the effect of this grayscale gene, it'll be tinted very lightly with that color. Same with gray, same with black, just tinted very lightly with the natural color. Those are the only instances where it's tinted and not full white, gray, or black. Other than that, if you get two N's, you will be completely unaffected by the grayscale gene, or excuse me, the dragon will be totally unaffected by the grayscale gene. And that's very likely with a fire dragon. Now, if you get two W's, you'll obviously have a white dragon. If you get a W and a gray gene, with the G here, then you will have a silver or light gray dragon. 2 G's is a medium gray. G and B is a dark gray, and 2 B's is a black dragon. So let's calculate this. 30 and 46. If I'm not mistaken, that's all. And yep, 30 and 46. That is all N. So the mother dragon has inherited a lot of dominant genes, almost all of them. You see how this affects most dragons. There is still a possibility of them becoming a blue dragon or having, or a black dragon. Both are very rare outcomes for this species. Actually, black even more rare than blue. So that being said, they still have the possibility to do this. So you can see the variation, but you can also see how most of these dragons will fit their norm description and random calculations of the first generation. And how that turns out. Alright, so let's put all of these calculations together. And we will see the base color of our dragon that all of these have contributed to for this lovely lady dragoness. Even though these lines will also be the same for the male later. Alright, so first of all, we got red. So we are in the red already, automatically go into here. And let's just select that just for fun. Now, after that, we have in the mixing, we ignore these genes right here because we'll pass them on, she'll pass them on to her young, but they're not going to be able to affect her because these two are the same, so the mixing genes are not going to affect her. However, the next ones, which are the brightness genes, will affect her. They're both bright, so that means that we're already pretty much right there. Now, the next ones are the saturation genes, and they're both S, which is full saturation, so we're still where we're supposed to be. Neutral on the grayscale, so actually she should be around anywhere in this little square area. Let's go right here. Just to make it not so bright, but it's still within that square of a small area that we should pick from. This is now the color of our dragon, and it's going to be all haphazard because I'm just going to paint it in rather than do the scale thing, because we'd have to color each scale with the paint bucket. It would take forever anyway, so this is pretty much what a little smaller. Pretty much what she'd look like, and I'll erase the other stuff anyway, but that is just to calculate this base color for the female. You know, most likely she could have yellow or something else for the underparts. You know, it's just, that's how long it takes just to calculate the base color, guys. So, I mean, I know I make things pretty complicated, but hey, you want variety, that's what you do. But this is also another perfect example why, for this species, red is the most common color. And, And I won't watch you, I won't make you watch me, excuse me, won't make you watch me color this whole thing and erase all the parts that are outside the lines, but you get the idea of how this stage goes.